make sure the concept is understandable. I take this one of the maybe which one? This one should be better, right? I can use this one to try to draw this graph, right? What's the spanning tree? Okay, let's do it this way. Assume that I have a one graph, right? For example, okay, let's say this is a one. I'm sorry about this. I don't have a such kind of efficient tools, but I can try to formalize my idea. Is this one 4, and then let's say this is 5. Okay, then so we have a relationship. Let's say such kind of relationship. Okay, so this is graph, right? I mean, what's it? This is graph. What's a spanning trees? As I said, same vertex. Okay, so same vertex, it means I have to include 1, 2, 3, 4, 5, right? So it means 1, 2, 3. Oh, there's a 3 here, 3, the 4, and 5. Okay, that's a spanning. I mean, I'm trying to come out this idea of how the spanning tree look like, right? Okay, so this is a vertex, same vertex. Then also also the edge size smaller than 1 in the graph of size of the vertex. Okay, so how many vertex? We have a 5 vertex, but there is a edge size should be smaller than 1. That means okay, 1, this is how many? 5, but should be smaller than 1, should be 4 edge. So make it 4 edge. 1, 2, 3, 1, 2, 3, 1, 2, 3, that's 4. Okay, if I need to do one more, then it's not become the spanning tree. Okay, that's the definition. I mean, this is a spanning tree, this is a spanning tree, this is a graph. Okay, of course, I mean, there is a not only the one spanning tree. I can create it another spanning tree, like for example, 1, 2, 3, 4, and 5. I mean, keep remember they has a same amount of the vertex, but 1 minus size of the edge. Okay, so now I'm going to different way. I'm going to take it this way. Okay, this is how many? 1, 2, 3, 4. That's not. This is another spanning tree. But spanning tree is not been looped. If I think, man, if I take this 1, 2, 3, 4, man, this is not being becoming spanning tree. What I'm saying is 1, 2, 3, 4, and 5. Okay, and this is 2. Come on, this is 2. Let me. This is 2. This is 1. Okay, if I make this relationship just like 1, 2, 3, and then even 4, it's not this. It's not this. Spanning tree. I'm not described yet, but it's becoming the cyclic. Okay, it is becoming the cyclic. So I will give you one more clear definition later on how we can avoid the cyclic, right? So okay, let's still 1, 2, 3, 4. 1, 2, 3. Then it should be one more. If I remember, there is should be already has such kind of things. Then 5. That should be kind of I mean, if I do this way, this is another spanning tree, right? This is another spanning tree. This is 5. Okay, so I think we have a 1, 2, 3 kind of spanning tree. Then I can also create another spanning tree as long as smaller size than 1 edge, then vertex in the graph. Okay, so this is the first step. How I can, this may be a little bit, maybe I can use mathematical way. Let's say graph is G. Okay, the graph is, maybe I can create another page, right? For example, graph is G, right? How we can represent the graph? Graph has 2 elements, right? Vertex and edge, right? Vertex and edge. And then what's the spanning tree? As I said, spanning tree also has, of course, vertex and edge. Should look like they're very, similar, but I'm trying to distinguish using the vertex prime and then E prime as a differentiated this the terminology. Okay, so if I am, this is a graph, this is a spanning tree. What's the spanning tree definition is they has a, vertex is same, v equal to v. Okay, that's a important one feature. Second is age size. I mean age prime, age size. Okay, let's say we make it the size. Okay, age size equal to vertex size of the graph. I mean, let's say the size v. I mean, this is not this is a graph of the vertex, right? The size of -1. That's then third one, don't make it cycle. Okay, don't make it cycle. Let's do this way. Okay, don't make it cycle. Okay, don't make it cycle. So if you satisfy the 3, and then it's just becoming the spanning tree. So this is a spanning tree. Okay, that's mathematical way. I mean, now, as I said, we have a, from the one graph to generate the three different spanning tree, right? From one graph, you can generate the 3 different spanning tree. Of course, I can create another spanning tree as well. It's also fine. Now, I'm wondering okay, I understood. Do you understand spanning tree, right? Okay, you understand the spanning tree, but what kind of things we can get benefit from the spanning tree, right? So there is one things that most in the everyday life mostly used it in the how we came from accessing from one city to another city, spending the less money, let's say, or maybe I can we create this one to create this country road as efficient as possible. So what does means efficient is as short as possible, right? From one city to another city, I'm driving the car, I'm spending less time. Okay, maybe the road is very good condition. I don't know. Maybe it's the bad condition. Depend on the between the one node to another node. Maybe has a from one city to another city should be has many node existed, right? So I'm wondering there should be something. Sometimes we expected to something efficient. Okay, maybe you want to spending less money to get there, or you want to spending to less time to get there, or you want to spending to short distance to get there. Doesn't matter. Okay, so there is a perspective difference. The more generalized that they have a between the, node to node, they expect something minimum risk. Okay, that's being called minimum spanning tree. Okay, let's call it the minimum spanning tree. Okay, let's call it minimum spanning tree, MST. Okay, so minimum spanning tree is that we're not interested all of the solution instead of one that very optimized. Okay, so there is a how we can know which one is optimized, right? Next question is which one is the minimum spanning tree that optimized. Okay, so okay, now as I said, from the one distance to from, for example, from 1 to 5, okay, 1 to 5, I can get from 1 to 5, 1 4 5, 1 3 4 5. Okay, there is a many way to you can get there. So as I said, between the one node to another node, they have a somehow relationship. For example, maybe let's say the road condition from this one is very good. So this is for me. This is the relation. Let's mark it one. Come on. Okay, this is one. Maybe there is a, let's call it, this is a two. There is maybe the condition should be 3, and then this is the condition also good. Maybe it also same as this one. 1. This one is very bad, so it's 4. This one is in the middle, maybe 3 as well. Okay, so you can see that. Let's count it. This cost from 1 to 5. This first one is a 3. Okay, the second one from 1 to 5 is 6, right? And then third one is 1. This is 4 and 1. How many? This is 5. Then this is 8, right? So they have a many choice, but there is not same cost, right? So this is interesting that, okay, I can able to calculate something between the relationship, which is sometimes being called weight. Okay, let's call it the weight. But as I said, this should be different. You can call it this is the ticket of the price or condition of the road, whatever the between the distance. So you can that we generalize that. Okay, just call it the weight. Okay. So this is weight. We can the terminology to weight. How much the weight total size? Depend on the weight total size, we can find minimum spanning tree. Okay, so that's the reason we are not interested all the spanning tree, but we interested minimum spanning tree. Okay, so for that case, let me do any color I can change. Can I change color? No, there is a possible to change color. Set background. No. Yeah, I can change color here. Now, maybe this application need that. Okay, maybe there is. Oh, good. So, this one. Okay, this is not the. It's also not changing the color. Okay, fine. As you can see, this is the first one. This is the first one, and then this is the second one, right? And then this is the third row. Okay, and then if you think about the first choices, first one, and some of the, first one, sum of the weight, how much? First one is 3, right? And second one is I mean 3, 3, 3, 3, 6, right? And then third one, sum of the weight. What's the third one? 1 to 3, 3 to 4, 4 to 5, right? So it's 4 plus 1, 5, 5 plus 3 is 8. So as you can see, which one is our better choice? First one, right? Because weight size is total weight size 3, right? Okay, I can count it this way. So it means the direct way is simple ways I can find all of the possible solution. Then I can compare the each of the result, then find the minimal spanning tree. Okay, that should be easy, but sometimes not efficient. You know, when I have a many choice, maybe for example in the global level, right? Or maybe the country level should be the choice should be if more than 100, more than 1,000. No, it is a very hard to people doing. Can I do it, done it with the computer, then use some algorithm can make it more quicker than that. Okay, there is actually has a two solution, two algorithm, which is our topic today's two algorithm, Kruskal and the Primus, guarantee that they find you the minimum spanning tree. Okay. Okay. So you understand why is Kruskal and Primus useful, right? Now, okay, what's the difference if I do any kind of difference? I mean, how can I? So we understand. Okay, we understand the spanning tree. Also, we understand how to create the minimum spanning tree. Okay, and the finding the minimum spanning tree, we have a two-way. Okay, one's the Kruskal. I mean, one is the Kruskal, another Prima. Okay, maybe can I copy paste? Okay, one's the Kruskal. Okay, another is the Prima. And yeah, I almost pre that's it, right? Primus. And just I needed to move this one. Okay, just okay. So we have a two different way, two algorithm. They will be found us the minimum spanning tree. Okay, but okay, if there is a two solution, do you any kind of maybe which one is better, right? Okay, first we needed to why I need to learn two algorithm if there is a same, right? Actually, there is a the efficiency is same. I mean, both are trying to find you the minimum spanning tree. Efficiency level is the same, but this is a kind of you can use it in the different case. Okay, you can use it in the sometimes I have to use this one, sometimes I have to use that one. Why is that for? Okay, I mean, okay, I needed to figure out the difference between the key and the M, key and the P. Okay, let's say Kruskal and the Kruskal and the Prima. Okay, that's kind of competition I have to, in my mind, okay, needed to choose. Okay, which one is good? I mean, Prima think, I mean, this both person, Prima think because, you know, I needed to start from the any vertex that who's I mean I start from the any vertex that I beginning to beginning to extend my pass with the smaller weight. What does means? Okay, beginning to smaller weight. Okay, what does means is that a Prima think I'm starting from the any node. Okay, let's say that start from the 2. Okay, I mean, no. Start from the any, okay, start from the any node or any edge should be smaller amount of cost. Maybe, okay, let's start from the 2 of the edge, I mean, edge or vertex. Then what we have a possible solution is 2 and 1. I mean, what does 2 and 1 is from 2 to 1 or 2 to 5, right? I mean, compare this one, they have different kind of weight, size, weight. I mean, one is 1, one is 2. Prima think I needed to always try to find smaller first, then consider next to extend my pass. This should be continuously. If I'm not continuously, I'm not, maybe I cannot form the chi. That's a Prima concern. Okay, Prima think if I'm not studying the smaller one, that should be continuously. I'm not concerning the which one is small, but I first consider the smaller first. So what does mean? If I start from 2, I have a 2 choice, 1 and 2. Then I can start from the 2. What does means I can, I mean, the first one is a 2 to 1. Then when I had 1, so come here, I have another extension. There is a 4, cost is 4 and 3, and then as well as 2, right? Right? I mean, when I come to the, we link this 2 and 2, right? And then from the 1 perspective, we have a 1 to 3, 1 to 4, and then of course 1 to 2 is already, we made a connection, so it's not big concern. But we also had this another, at the beginning we had a 2, right? Because also we already had this node, there should be possible node 2. So considering the weight to 2, 3, and 4, which one is smaller? 2 is smaller. So second step is they going to extend to from the 2 to 5. Okay. When you come to the 5, we had another choices 5 to 4. Okay, 5 to 4, and then of course we had 1 to 4 and 1 to 3. Which one is smaller? Of course, the both are the same. And then the both are same, depend on choice. We need to pick it one. Okay, doesn't matter which one because it's the same. If you choose this one, okay, if you choose from 1 to 4, then you cannot choose the 3. Why? They connected, that make the cycle. Okay, so make the cycle, it means it's not become this spanning chain. The reason is that we had to, we needed to using the spanning tree, but okay, using make sure that they will be generate spanning tree. If you make this cycle, it means this becoming the graph. I mean, it's not becoming the tree. So we needed to avoid the cycle. So that's the reason either the one, or you need to choose one. There is a cost the same. Or if you choose the 1 to 3, then you need to ignore this 4 to 5. Then what's next is after that, if you choose the 1 to 3, next is, of course, next is 1 to 4. Okay. So then, of course, I cannot to choose 3 to 4, right? Because this is already, if I choose the 3 to 4, becoming the cycle, right? So the choice is that this one, this one, this one, and this one. So this is a kind of the Prima creating the spanning tree. So I can draw here in this middle. Okay, I choose is the P. The P is find the spanning tree is, let's say, I'm using the, I should use the pass, but instead, can I, okay, let's do it this way. First one is the 2 to 1, right? Just follow me, okay? First one is a 2 to 1, 2 to 1, okay? First one is 2 to 1. So what's the next cost? Smaller cost? It is a 2 to 5, right? Second one should be 2 to 5. And then what's the third one? It should be, okay, you need to choose either the 1 to 4 or 5 to 3. Okay, let's do it this 5 to 3. Okay, if 5 to 3, 5 to 3, it means I should give up the 1 to 4, because if I choose that, they become the cycle. Then continue to, I had choose, of course, there is a, which one is smaller? 3 to 4 is smaller one compared to 1 to 4, right? This is 1, right? So it means 4 to 3. Okay, this is a prima, so the result. Maybe, okay, if you think this is a prima, what's the Kruskal think? Okay, let's compare the Kruskal idea. Kruskal think, I can start from the, I needed to find all of the weight. First, I need to discard all of the weight. They think you need to discard for all of them. For example, 1, 2, 3, 3, 4, and 1. There's all of the option. I needed to store something in the collection. Then I needed to, start from the smallest one. Then what's the next smallest one? I don't care if there is a connect or not. Finally, same time, I needed to check it when you make this joint. Okay, that's a different idea than Prima. Prima think continuously. If not continue, then what's the Prima worry about is Prima worry about it. If I'm not continuously, maybe finally they cannot form the tree, because trees continuously linked together, right? And then but Kruskal doesn't care about this, the idea. They care about finally I can make it this work. If I cannot make this work, okay, it should be, otherwise I cannot find. I mean, if I find the result, misses work, right? But Kruskal is coming to this way. Kruskal, let's draw this way, okay? Let's say K, okay? What's the Kruskal think? Kruskal think, okay, at the first is, I'm starting from the cost is 1, okay? Then what's next? Are you follow me? Okay, repeat again. Kruskal think differently. Kruskal think, as long as I concerning my cost, right? As long as I concerning my cost. So how about I always, each time, step by step, pick this minimum one. So first I need to start from the most minimum cost of the option is 1 to 2 or 3 to 4, because both are 1, right? So you can start from the 3 to 4 or 1 to 2, doesn't matter. Let's start from 3 to 4. If I start from the 3 to 4, then what's next? Okay, I repeat again the idea of the Kruskal. Kruskal doesn't care about this connection, doesn't care about this continuously. They care about this, which one is a small one, which one is smaller cost. I mean, so at the first they have to visit all of the node. It means you need to recursively find all of them. Then you find all of the weight and the age. For example, 1, 2, 3. This is 3. This is 1. This is 4. All of the cost between the relationship. I storing something collection. Maybe I can store in the array, or you can store it in the linked list. Okay, that's don't think about that the first. The the performance, okay? Later on, we think about if there is a too much operation delayed or something, you can take this linked list. If not, deletion operation doesn't exist or deletion, just take this array. Doesn't matter. So just think about that first. Just put this our array, okay? Put this all of them in the array. The same time is between the relationship. Then first choice is of course smaller one, 3 to 4. What's next? What I told about if I starting from the 3 to 4, because this is a 1, right? If I'm starting from this position, what's the next? One to 2, right? You're saying right. You no doubt. Even this is not connected, 3 to 4 and then 1 to 4 is no directly connected. It's fine because this is the small one. So what does means is, okay, let me draw it here. Okay, 3 to 4. 3 to 4. This is 1. What's next is 1 to 2. Because this is another second one is a small one. Then what's the next? What's the next? 2 to 5, correct. 2 to 5. 2 to 5. Keep remember, if becoming the cycle, you have to escape, right? But this is a 2, right? What's next? Let me show you. What's next? How many choice we have now? Not only the one, there's has 2 choice. 1 to 4 or 5 to 4. Either one, because both cost the same. Both cost the same. If I choosing 1 to 4, okay. If I choosing 1 to 4, this is 3, right? Okay, there is interesting. What's next? Right. If I choosing, of course, should be I would be choose 4 to 5, but they become cycle, so I have to avoid it, right? So I have to avoid it. I shouldn't be choose 4 to 5. So what's next? I cannot choose the 4 to 5 because of the becoming cycle. So what's next is 4 to 3. No. This 4 to 3 already been chosen. Which one is? I mean, uh, uh, right. How many? 1, 2, 3, 4, 5. Now we already have a 4 vertex. So it's already enough. We don't have a other choice. I know that's a spanning tree. So that's of result of the Kruskal doing. Kruskal doing is that 1 to 2, 1 to 2, 2 to 5, and then 1 to 4, and then finally 4 to 3. 4 to 3. That's another choice. I mean, this is a cost is cost 1. This is 2. This is 3. This should be 1. I mean, you need to count it from that one. This should be smaller one all the time. I mean, this is also, you also counted this one. I mean, 1 to 2 to 1. 2 to 1 is 1. 2 to 5 is 2 to 5 is 2. 2 to 5 is 2. 5 to 3. 5 to 3 is 3. 43 is 1. If you count it, total is 367, right? And then this is how much? 2, 5. Hold on. There should be equal. What is my okay? 1. It should be. Hold on. All right. Also same, right? It is 7. That should be same. Otherwise, we doing not correct. This is 7. This is also 7. As you can see, this is 4, and then 3. This is also 7. The weight 7. Okay. As you can see, we used two different algorithm, but get the same result. Of course, not that exactly same, but this is a minimum cost the same, right? So, okay, good. Now, wondering, okay, if you, next question is, if you both are equal, you know, they found in the equal result, when I use the Kruskal, when I use the Prima, right? Then, as you can see, Kruskal doesn't care the, continuous relationship. It means I can skip the graph, right? That's a very good point, that even I can continuously concerning two graph same time. I can finally, there is a one graph, there is another graph, then I can find it even inside of the past, then concerning finally connect together, find the minimal spanning tree. But Prima cannot do that. Prima only the one graph been constrained. So that's very distinct difference. That's the place that you can use it. Okay, if you are, otherwise if you same graph, you can apply both them. But if you are, for a different graph, there is a choice only how Kruskal that does. Okay, so I think the terminology, the concept should be enough to understandable, right? Okay, so maybe we can take a rest. Then next hour we can concern how to implement in the coding level. Okay. Okay, take a break. Let me set up the time for attendance. Do you mind? I have to continue it. Then can leave it earlier. Can you do it? I just wondering that because I recording, otherwise I have to stop it. No. Okay, fine. I needed to stop it.